Today what we will do is we will discuss multistage graph. So this is one more problem in dynamic programming technique. So where dynamic programming technique can be used to solve this kind of optimization problems. But before doing that, so we had a problem which was being discussed in our previous session, that is on OBST, that is optimal binary search tree.
Yes, sir.
So main concept of optimal binary search tree is to find out the minimal value to be distributed both on either on the left hand side or the right hand side. So if we have multiple options of distribution, so we will pick out one key and try to divide the load towards left hand side and right hand side. So if key is k, then distribution will be on the left hand side, I to k minus 1 will be the keys will be there on the left hand side, and similarly on the right hand side we will be having k plus 1 to j number of keys, where I to j are ordered keys. So we had a problem of this, am I right?
Yes, sir.
Okay, so when we have a problem of this, so our main equation is C of ij will be equal to C of ik plus C of kj plus summation of probabilities of keys running from I to j. Okay, so where here k, picking out k is in between I to j. Okay, and we construct two tables here. One is cost table and the other one is root table. Cost table basically will give us optimal value at the end of this, and a root table will give us the way where we can construct optimal binary search tree. Initially, in the root table, it will run from if it is 5 keys, so it will be having 6 cross 6 matrix, where the columns will be running from 0 to 5 and rows will be running from 1 to 6, that is 1 to n. The same way here also in the root table. And principal diagonal axis here is 0. The reason is 1 to 0. So we cannot have keys starting from 1 and ending at 0. So it has to be always incremental. Keys has to be in an incremental fashion. So therefore, there is no option for us to construct a tree. So therefore, its optimal value remains as 0. In the root table, the principal diagonal axis, we will leave it as empty. The reason here in this case is we have not constructed a tree, and there is no option for us to choose key. Then second diagonal after the principal diagonal axis, which we call it as stage 1. So here in this case, what we have done is we have one key, that is 1 to 1. We have one key, so we can construct only one tree out of that. So therefore, the probability remains as the probability of that key itself. And as the key is remaining in the root, so therefore root 1 comparison into 0.25 remains as 0.25 itself. If you same way compare the root table, so it will remain as one key. There are no other ambiguity. So it is one key tree. Same way 2 comma 2 cost table will be one key, 3 comma 3 one key, 4 comma 4 one key, 5 comma 5 one key. So this is the initial state for us. Then from stage 2 onwards, we will get a computators. Means to say that when it is a single key, there are no much computation. Means to say that there are no ambiguity. But when there is more than one key, then the ambiguity arises. Which to choose a key among them. So the principal diagonal axis completed. After the first diagonal we have completed, we have to complete now second diagonal. So second diagonal will contain 1 comma 2, 2 comma 3, 3 comma 4 and 4 comma 5. So we need to solve these 4 subproblems. So to solve 1 comma 2, as you can see, I hope so you can see this calculation. So for 1 comma 2, we have an option of choosing key as 1, or we have an option of choosing key as 2. If we choose option as key as 1, then k will be equal to 1. So according to the formula, so it is C of I k minus 1 plus C of k plus 1 to j. So C of I is nothing but 1, k minus 1 is 1 minus 1, 0, plus C of k plus 1. K plus 1 is 1 plus 1, 2, comma 2. So we need to have these two cell values, that is C of 1 comma 0 and C of 2 comma 2. Same way, when key becomes 2, then our equation becomes C of I comma k minus 1, that is 1 comma 2 minus 1, that is 1 comma 1, plus C of k plus 1 to j, that is 2 plus 1, that is 3, 3 to j, j is 2. So we'll get these two values plus summation of probability of keys from 1 to 2. So if we solve this, so 1 to 0, we don't have any tree construction. So therefore it's, average probability becomes 0. Then C of 2 comma 2 is 0.2. Likewise, C of 1 comma 1 is 0.25 and C of 3 comma 2 is 0. So among them, the least one is first key. So therefore, first key is the least one. So we'll take that and summation along with the probability of key 1 and 2, that is 0.45. So we get a value of 0.65. Hope so you're getting the same answer.
Yes,
you would have got the same answer. Okay.
Yes, sir.
Same way, C of 2 comma 3, we have two keys, 2 and 3. So among them, we need to construct a tree. So this also follows in the same way. That is C of I comma k plus 1, and sorry, k minus 1 plus C of k plus 1 to j. Same way here too. So we get a profit of 0.3. Are you getting?
Yes, sir.
Okay. So how about C of 3 comma 4?
0.3.
0.3 you have got.
Yes, sir.
And same way C of 4 comma 5.
0.7.
0.7. So here you can see that for constructing C of 1 comma 2, which will be the key or the root node?
1.
1. 1 will be the root node and 2 will be either on the left or right.
Yeah.
So 2 is greater than 1. So therefore it has to be lying on the right side. So right side of the key, that is k, 1. Same way, 2 comma 3, C of 2 comma 3. Here you can see that which key we have chosen as a root?
2.
So we have chosen as root. So therefore we will get 2 as a root and 3 will be the right child of that. In the same way, C of 3 comma 4.
4.
4 is the root. So therefore if 4 is the root, 3 becomes the left child of that.
Yeah.
4 comma 5.
5, sir.
So 4 comma 5, here 5 is the root. So therefore we will get 4 as left child of that.
Yes, sir.
Fine. So we get a tree construction, partially constructed tree, looks like this. So our second stage we have filled with the values which you have got, that is 1 comma 2, 2 comma 3, 3 comma 4, 4 comma 5. So their probabilities, comparison average values, and similarly the key which we have chosen. So in 1 comma 2 we have chosen key 1. So therefore 2 lies in the right side of that. So right child. Same way 2 comma 3 we have chosen 2 as key. So therefore 3 becomes the right child of that. In the same way 3 comma 4, 4 we have chosen as the key. So therefore 3 becomes the left child of that. In the same way 4 comma 5, 5 is chosen as the root node. So therefore we get 4 as the left child. So this is, we have completed second stage. Am I right? Hope so you have
Yes,
got
sir.
the same answer.
Yes, sir.
Then similarly, the third stage. So we will get 3 keys, that is 1, 2, 3. So 1 comma 3 will be filled by 3 keys, that is 1, 2, 3, their search probability. Same way 2 comma 4, that is 2, 3, 4. Likewise 3 comma 5, 3, 4, 5. So we will get, every time you complete one diagonal, so we are adding 1 key into our tree. Okay, so we need to solve now 1 comma 3, 2 comma 4 and 3 comma 5. So C of 1 comma 3. Now we have 3 options here. Either we can choose key as 1 or key as 2 or key as 3. So if we choose key as 1, so we'll get C of 1 comma 0 plus C of 2 comma 3. If we choose key as 2, then we'll get cost of 1 comma 1, then C of cost of 3 comma 3 and so on. So here you can see that the least value which we have chosen is
0.3.
um, we will get this as
So there will be collisions, and then what will be
Yes,
the
exactly here.
0.3 and
So we
0.3
have two options here, right? So either we can choose key as 1
or 2.
or key as 2. So there is, there is a provision for both. You can choose either key as 1 or key as 2. So we'll keep that option as it is. Okay, so but overall our minimum value becomes 0.3, and the summation of all the other probabilities running from 1 to 3 will be 0.5. So totally we'll get a value of 0.8. Am I right? The same thing happens with keys from 2 to 4. So here keys from 2 to 4, do we have any ambiguity? Any collision?
Yes, sir.
Yeah.
Yes, sir.
Here also we have a collision. That is nothing but either you can choose key as 2 as a root node or key as 4 as a root node. So there is a provision for both. Same way in the case of 3, 5. So do we have any collision?
No, sir, there's no collision.
Here we don't have collision. So therefore, here it is unanimous that key 5 will become the root of this. So once we construct the tree, fill the table and construct the tree, you can see here that in 1, 3, we had an option of either 1 or 2. If we choose 1, then 2, 3 will be on the right hand side of 1. So to choose among 2 to 3, so we use this root table. In 2 to 3 cell, you're able to see the pointer?
Yes, sir.
Yeah, in 2 to 3 cell, you can see that 2 is a root. So therefore, the root of that right subtree becomes 2. And the leftover is 3. 3 is greater than 2. So therefore, automatically it becomes a right. So therefore, we get a skew tree almost. It is a right heavy tree. Right? So the first option, if we choose key as 1. If we choose key as 2, so among 1, 3, so 2 becomes at the root node and 1 will be on the left hand side. So there are no other computator, as well as on the right hand side we have 3, no other computator. So it becomes simpler, clear. Am I right?
Yes, sir.
In the same way, when we have 2, 4, in the 2, 4, you can see that either key 2 can be root or
Key 4.
Key 4 can be root. So if key 2 is root, then we are left out with 3 and 4 on the right hand side. So in the 3 and 4 on the right hand side, so we need to find out which is among that will be the root of the right tree. So 3 to 4, you can check out here in the root. 3 to 4, we have 4 as the root. So therefore 4 will become the root of the right subtree. So if 4 is the root of the right subtree, then 3 is left out. So 3 is smaller than 4. So therefore 3 has to come on the left hand side. Are you following?
Yes, sir.
So the same case, even in the place of if you choose the key 4 as a root. So if you choose key 4 as a root, then leftover vertices are leftover nodes are 2 and 3. So among 2 and 3, so we will check out from 2 to 3 which is the root. From 2 to 3, that is 2 is row and 3 is column. You can see this in the root table, we have 2. So therefore 2 becomes a right subtree's root or parent. And then therefore the leftover one is key 3. So key 3 is the alone one. Therefore there are no more computations. So it will become the right child of 2. That is in the case of 2 cases of 2 to 4. In the case of 3 to 5, so we don't have collisions here. So it is a single tree. So 5 is the root. So 3 to 5 means 3 and 4 are the 2 values which we have. So therefore 3 and 4, among 3 to 4, we will check row 3 and column 4. So we can see that 4 is the root. So 4 is taken as the parent of the right subtree, and therefore leftover is 3. So we get this. So there is a provision like, when you have same values, cost values, which are being generated in the cost table. In that case, if there are more than one keys being chosen having the same cost value, then there is a provision equal probability will be there to design whichever the key you want to take.
Okay,
So
sir.
we will try to draw both. Fine.
Okay, sir.
Then we need to fill down 1 to 4 and 2 to 5.
Hmm.
That is next diagonal. That is stage 4. Next diagonal we need to fill. That is 1 to 4 and 2 to 5. So in 1 to 4, we'll get 4 options. That is, key can be 1, or key can be 2, or key can be 3, or key can also be 4. So in all these 4 options, you can see that. So the best key chosen is,
2.
so we'll get 0.55 is the best key, and compared to all the other, like first one is 0.75, second one is 0.55, third one is 0.85, and fourth one is 0.8. So comparing all this, so key 2 is the best choice. So therefore its cost value is 0.55 plus its total probability, that is running from 1 to 4, total probability is 0.7. Same way in the case of 2 to 5. So 2 to 5, we have key 2, key 3, key 4, and key 5 are being chosen. So when you list down, so we'll get a least value. 0.6 is the least value. So 0.6 stands for which key? Key 4.
Yes, sir. Key 4.
So key 4. So in the first case, 1 to 4, it is key 2. And the second case, we have key 4. So therefore, according to this, we will fill the cost table as well as root table. So we have 1.25 and 1.35 as values, and the respective keys are 2 and 4. So here I have constructed a single, tree, that is 1 to 4 I have constructed. I think I have left for you to construct 2 to 5. So 1 to 4, when we are constructing, you can see that 1 to 4 root 2, key 2 becomes the root of this tree. And on the left hand side, we have only one key. So therefore there are no much ambiguity. And on the right hand side, we have 2 keys, that is 3 and 4. Once again, which to be chosen as a parent of this. So therefore, we will check in the third row and fourth column. We can see that we have key 4. So therefore, among 3 and 4, we will choose 4 as a parent and 3 as a child. So we get a tree of this kind. Can you draw a tree for 2 to 5? So 2 to 5, which is the root?
4.
So root becomes 4. So if 4 is the root, then on the right hand side of 4, unanimously 5 is the right child. So there are no more computation. And on the left hand side, we have 2 keys, that is 2 and 3. Among 2 and 3, which should be chosen as parent?
2.
2. So 2 can be chosen as parent. So if we choose 2 as parent, 3 will be right child of 2. Fine. So till here it is fine.
Yes, sir.
So all of you got that. So 4 is the root, right child is 5, left child of 4 is 2, and the right child of 2 is 3. Then in the stage 5 is, now we will take optimal binary search tree for 1 to 5.
Yes.
So the last cell need to be filled. So the options here is, when you choose 1 to 5, you can choose key as 1 or key as 2, as key as 3, 4, 5. And in each of these, you can see that we are taking, like, for example, 2 to 5. We have already calculated. 3 to 5, we have already calculated. 4 to 5, we have already calculated. So the calculated values we are taking to find out the final value. So in every time after the first stage onwards, we'll be taking the assistance from already calculated sub-problems values. Fine. So we get a value of 2.1. So 1.1 is the least value. So 1.1 we get it from key is equal to 2 as well as
4.
key is equal to 4. So we have to get 2 trees now. Am I right?
Yes, sir.
So we get 2 optimal trees. So either you can choose key 2 or key 4 as the root of this tree. So therefore, if we choose either 2 or 4, so if we choose key 2, okay, if we choose, okay, I have chosen now key 4. So if we choose key 4 in the beginning, then 4 as a root, on the right hand side, you have more than 4, that is 5. So unanimously you can stay. And on the left hand side, it is 1 to 3. Now, once again, you can see that in 1 to 3, that is first row and third column, we have an option. Either we can choose either 1 as a root, I mean parent among that, or 2 as a parent among that. So if we choose 1 as a parent among that, then 2, 3 has to lie on the right hand side of 1. So once again, among that 2, 3, we will try to check. That is second row and third column. So we get among 2, 3, 2 as the root. So 2 as a parent. So we will take 2 as a parent. Then 3 is larger than 2, so that becomes the right check. So we get 1 tree of this kind. Then in the same way, choosing either 1 or 2 as a parent. If we try to choose 2 as a parent, 2 as a parent, so therefore we get 1 on the left hand side and 3 on the right hand. So we get this kind of tree. So that is in the case when we have chosen 4 as a root. Okay, 4 as a root. Suppose if we choose 2 as a root, then we will get 2 on the left hand side of 2 less than 2 is 1. So we have 1 key, single key, so that can be made as left child. And on the right hand side, we have 3 keys, that is 3, 4, 5. Now we need to check 3 to 5, third row and fifth column. So which can be, so 5. So 5 will be made as a parent among 3, 4, 5. So if 5 is the parent, then 3, 4 has to lie on the left hand side. So therefore, we have 3, 4 among 3, 4. Third row and fourth column, we have root 4. So therefore, among 3, 4, 4 becomes the parent and 3 becomes the left child. Fine, I think last 2 are once again redundancy. Correct. So is it fine? So whenever you have clashes, we have to consider both the cases and we have to explore both the cases. Luckily, we are stuck with only 2. Suppose if we go for 3 keys and all the 3 keys qualifies to the same value, then we have to construct, we have an opportunity to construct more than 1 tree. So we can go for 3 trees. Fine. Any doubts in this?
No, sir.
No? I think hope so. Most of you would have got the similar kind of answers.
Sir, so for this sum, we are constructing 3 optimal binary search trees, sir.
Yeah, almost at the end, we'll end up with 3 optimal binary search trees.
Okay.
And all the 3 optimal binary search tree will have the average probability search value as 2.1. You can cross verify that also. Like for example, if you start from the root is 4. 4's value is 0.2. 0.2 into first comparison, 1 comparison. Okay. Then for the next key 1, we have 0.25,
Huh?
0.25 into two comparisons.
Pump was and Mara.
So your voice is not audible, sir.
So Janardhan sir, your voice, you muted yourself.
Yes, now?
Yes, sir.
Yeah, for 5, we have a probability as 0.3, and as it lies in the second comparison, 0.3 into 2. So we'll get 0.6. So we'll get 0.5, 0.6, and 0.2. Similarly, 2, key 2 is at the third comparison. So therefore, key 2's probability is 0.2, 0.2 into 3, that it becomes 0.6. And key 3 is having a probability of 0.05. So 0.05, and how many number of comparisons? 4 comparisons.
Yes, sir.
0.05 into 4 comparisons. So total summation, are we getting 2.1?
Yes, sir.
We are getting. So you can also check for other trees also. So for all the other trees also, we will get in the similar way 2.1 as our comparison value.